This video will focus on a new concentration unit called molality, and we'll do problems on that. And then we'll also look at how concentration can be used in stoichiometric calculations to solve for unknown variables. So molality, which as a unit is a small m rather than uppercase M, is still a concentration unit. So it's still relating solute to something. But in this case, it's moles of solute per kilograms of solvent. So the denominator changes when you compare it to molarity, which is per liters of total solution. The reason why we need a molality calculation in this unit and aren't just going to use molarity is because of the effect of temperature on concentration. Molality is not affected by temperature change. Okay? The mass is independent of temperature, where the volume, we know, does have a relationship with temperature. As you increase your temperature, your volume can increase in terms of the space it takes up. So eventually, when we look at colligative properties later this week, which is a topic that specifically focuses on how temperature change is affected by having a solution, it's important that our concentration is independent of that. So molality, small m, is moles of solute per kilograms of solvent. Problems for this are no harder than the problems for molarity. It's just a question of keeping what you're looking for and what you have straight and keeping this relationship well established. So here's two different practice problems we're going to look at. Let's go. So again, molality is moles of solute per kilograms of solvent. So when given a problem, one thing to keep in mind is you really got to focus on what is your solute and what's your solvent. Because unlike molarity, they're going to be measured in the same thing. You're going to get both numbers in masses rather than one in volume, so you got to keep it straight. When you read this problem, it says that benzene dissolves into acetone, which means benzene is my solute and acetone is my solvent, because benzene is dissolving into acetone. Okay, I have 500 grams of acetone, and then I'm also given the molality of this solution. So first of all, I've given acetone, and acetone needs to be in kilograms for me to use this relationship. So I'm going to make that 500 grams into kilograms first, which is 0.5. I'm also given the molality here, which is I have 1.25 moles then per every 1 kilogram. We can use this as a conversion factor then to get from kilograms of acetone to moles of benzene, which will then allow me to get to grams, because once I have moles, I essentially have grams because of molar mass. So if I multiply this by the molality, which is 1.25 moles per 1 kilogram, that gets me to benzene, and then I can go mole to gram for my last step using that molar mass of benzene. Multiply that out, you should get that you have a mass of 48.82 grams of benzene in that 500 grams of acetone. Next problem asks us to simply calculate molality, which again is moles of solute per kilograms of solvent. So when I read it, it says calcium chloride is dissolved into water, which means your calcium chloride is your solute and your water is your solvent. So I'm given grams of water. I can get that to kilogram, dividing by 1,000. And then I need moles of solute, and I'm not given moles of solute, right? I'm given grams. But if I'm given grams, I can get that to mole fairly simply by using the molar mass. So there's my number of moles of solute. There's my kilograms of solvent. Divide, and that will give me my molality of 0.9442. Small m is molality. Okay, so I have a 0.9442 molal solution. These are the molarity problems. It doesn't get any harder than this. It's just a subset of colligative property problems that we'll get to later this week. The other thing about this unit is we can use concentration as part of our stoichiometry. Okay, in the past we went like gram to mole, mole to mole, mole to gram. Molarity is another way to get to mole, or molality would be a way to get to mole. So instead of starting out in grams, we can start out in volume and then use our concentration as a way to convert. This simply expands our way of being able to use stoichiometry in a lab setting to do calculations. So here's an example problem. Asked me to calculate the volume of an aluminum sulfate solution, that's that concentration, that can completely react with 75 mils of a calcium hydroxide solution. So here's the information you have. You're just dealing with your two reactants. And the question is, if I have 75 mils of my 0.325 molar solution, how much solution do I need to react with it if I have a 0.233 molar solution of the other reactant to make these two things completely go away? So how this works is this is my starting amount, okay? I know I have 75 mils of that calcium hydroxide, which I'm actually going to move into liters right away because we know our molarity is moles per liter. So I know I have 0.075 liters of calcium hydroxide. And the question is, with 0.075 liters of calcium hydroxide, how many liters of the aluminum sulfate do I need? To use stoichiometry, we need to get to a mole-to-mole ratio. So that's why we use our concentration. Our concentration relates liter to mole to get us to mole to allow us to use mole-to-mole relationship. So this concentration is that for every 1 liter, I have 0.325 moles. And then I'm going to go mole to mole, so moles of calcium hydroxide, into moles of aluminum sulfate. And that relationship is the coefficients, so every 1 I get 3. That gets me moles of aluminum sulfate, but I don't want moles, I want liters. And in the past, we went mole to gram using molar mass. Now we're going to go mole to liter using the concentration of the given solution. So our last step is moles per liter of aluminum sulfate. For every 1 liter, the concentration is 0.233. Still a 3-step stoichiometry problem, similar to what we're used to. It's just that we're using concentration instead of molar mass. So multiply this out, you should get 0.0349 liters or 34.9 milliliters. So I need 34.9 milliliters of this solution to react with 75 mils of this solution so that they totally react together and there's no amounts left over. Now we can combine our stoichiometry with other types of calculations. So the first one here, if I made a solution by taking 16 mils of a concentrated solution and diluting it, that means this first problem is an M1V1 problem. Okay. I've got 16 mils of my concentrated solution. And the question is, what is my new concentration if I dilute that to a volume of 550? So M1V1 equals M2V2. Solve for your M2, you'll get a concentration of 0.15 big M. So now the question is, if I'm going to take that solution and react it with 26 grams of zinc, how much do I need? So again, to completely react them. So I have a 0.15 molar solution, and I don't know what my volume is. It's still just stoichiometry. You never start with a concentration because that's a conversion factor, same as you never start with a molar mass. You start with a measured quantity. I have 26 grams of zinc. I can go from grams to moles of zinc using molar mass. Once I'm in moles of zinc, I can go 2 moles of a new thing, my hydrochloric acid, and this is just my relationship established by my reaction. Once I'm in moles of hydrochloric acid, I can go 2 liters of hydrochloric acid given a concentration. So for every 1 liter, I calculated I have 0.15 moles. That will get me to volume, which is what I'm solving for. So if you multiply this out, you should calculate that you need 5.3 liters of HCl to react with 26 grams of zinc. There's lots of different ways that I can continue to use concentration in stoichiometry problems. These are 2 examples. We're also going to do a lab where we're mixing solutions and we need to predict what would happen given limiting reactants and percent yield. So just like we did for stoichiometry, except using concentrations now. That's it. go ahead and do the form, and I'll see you tomorrow.